Today, we want to talk a little bit more about this derivative and what we can do with the derivative. Right now, our primary motivation is just to find the slope of the line tangent to a function at a given point. This is the one thing that we have for the derivative. But we want to find out some more things. In kind of simplistic terms, we're finding the slope of a tangent line. So anything that we can do, anything that the slope is going to tell us, that's what the derivative is going to tell us. Applications of the derivative are just going to be applications of slope. That's the biggest key. Is that the derivative tells us the slope of a line. So from an overly simplified standpoint, applications of slope are applications of the derivative. Anything that a slope is telling us is something that a derivative will be telling us. So that means it makes sense for us to talk about what the slope represents. So anytime we were talking about slope in the past, it's now something that we can talk about with the derivative. The same thing happens when we get to integration. Integration is just multiplication, but one of the factors is continuously variable. That means that any applications of multiplication, anytime you use multiplication in a practical sense, you can turn it into a calculus problem by making one of the factors in the multiplication continuously variable. The same thing is going on here. Way back when you talked about slope, now we're going to talk more about slope because that's all that we get with derivatives. Applications of slope are applications of the derivative. So what is the slope? Take out the comma, and this is like most of the student comments. So what? But I got to put a comma in, make it more relevant. So what does the slope tell us? So let's think about the slope. Slope is rise over run. That's more of a graphing thing. It's the change in y divided by the change in x. When we have these deltas and we have the slope connecting 2 points, that's going to be the average rate of change of y with respect to x. So we're going to say this is the rate of change of y with respect to x. For 2 points, if you have two separate points, you're going to be looking at the average rate of change of y with respect to x. So if you have 2 points, which equation? I said delta y over delta x equals rate of change of y with respect to x. So we want to make a distinction with the rates of change that we have. If we have two distinct points, we're looking at an average rate of change. For example, if I hop in the car and I drive 400 miles and it takes me 5 hours, my average, that's kind of fast. If I go 300 miles in 5 hours, my average speed was 60 miles per hour. That doesn't mean that at every point on that trip, I was going 60 miles per hour. Sometimes I was probably going faster, and sometimes I was probably going slower. If I started the trip from here in the parking lot, it would be super irresponsible to be traveling at 60 miles an hour before I got to 280 up there. Actually, there's that stretch of skyline where you can kind of accelerate a little bit more. You're going downhill. So, but the speed limit is 50, and I never go over the speed limit ever. Clearly, I'm lying because I'm saying my average speed was 60 miles per hour. I most definitely was speeding at some point. So that's just your average because there's 2 points. You just looked at the total amount of distance divided by the total amount of time, average 60 miles per hour. If we're taking derivatives, if we have a tangent line, that's going to be our instantaneous rate of change. So using the previous example, that would be your speedometer reading at a particular point. My speedometer reading when I'm driving through the parking lot will say 15 miles per hour because I'm being responsible and safe. Then when I get out on the skyline, the speed limit is up, it goes up to 50. So I'll be going, my speedometer will be saying my instantaneous rate of change is 50 miles per hour. So I'm being responsible and safe. Then when I get up onto 280, I'll be traveling at highway speeds. It's like, I'm gonna go with 65 miles per hour as my instantaneous rate of change. So overall, I'll have an average speed for the entire trip, but at different points, that instantaneous speed will be higher or lower. So in 2 points, you're talking about an average rate of change. With your tangent line, you're talking about an instantaneous rate of change. So we could think of our tangent line like a speedometer. I love that when we invented the word speedometer, we put the O in the middle and didn't just call it a speed meter. Named it like a carnival ride. Tilt-o-whirl. Throw that extra syllable in there. Speed-o-meter. Every time I see the word speedometer, I want to think about that transatlantic voice that they used in the 40s. Check out the new speed-o-meter. See how fast you're going at any instantaneous. Yeah, I can't actually do the voice. It's very uncomfortable. Part of it is because it comes from the 40s and I couldn't have existed in the 40s, at least not in this position. So your average rate of change, that's the slope that you dealt with before. That's just going between 2 points and connecting them with a line. Your tangent line is going to be your instantaneous rate of change. So instead of delta y over delta x, we'll write dy over dx because delta y and delta x become infinitely small. One of the ways that we can interpret the derivative is to just interpret the slope along with the derivative. So we need to talk about how to make units of slope. The slope is just delta y over delta x. Y has some units. X has some units. So the units of the slope we just take the units of y, we write the word per, and then we write the units of x. To make the units of slope, you write the units of y, then you write the word per, then you write the units of x. Per is just a word that means divided by. Percent means divide by 100 or per 100. So to figure out the percent, you just divide by 100. So think of per as divided by. This makes it easy to remember. This makes it easy to remember if we just think of per as divided by, because that's how we build the slope. We take y per x. That's all the slope is telling us, how much change in y per unit of x. I almost wrote y for y. So for example, y is distance in miles after x hours. So y is measuring a distance, measured in distance in miles. So the units of y are miles, and the units of x are hours. So delta y over delta x will be miles per hour. So the units of the slope right, the units of y per units of x. Then you look at what those units represent and say, oh, we are measuring speed. Speed is the rate of change of distance with respect to time. So this makes sense with stuff that we already know. Speed is the rate of change of distance with respect to time. That fits with stuff that we already understand. Speed is the rate of change of distance with respect to time. Speed is distance divided by time. We've been doing calculus all along. It's like Palmolive. I don't want to use units, even though units is better. Let's say X items. So we're running a business, we produce items that we then turn around and sell. It costs us money to produce those items. C of X will be the cost in dollars of producing X number of items. So the units of output are the units of Y. are going to be dollars, and the units of X is just number of items. So the units of the slope will be dollars per item. This will represent how our costs will change if we increase the number of items we produce by 1. Sometimes this is referred to as the marginal cost. So this could, if this is negative, that means producing more items, it would cost less per item. Increase our costs because we're making more items, but the cost per item would be lower. Or we might be at a point where if we increase production, it will cost us more. Think about buying things in bulk. If you agree to buy 1,000 units, I will give you a lower price per unit. Any questions? Now, those business majors among you might find my description of marginal cost lacking. This is because I am not versed in business. I'm just putting math things together. I just go around to different fields, grab the derivatives where I see them, and throw them through this kind of analysis. How do we make the units? Does that make sense? I understand the distance equal to rate times time thing pretty well from physics, but there are a lot of other things that my explanations are going to be lacking. This is generally considered a failing among all mathematicians. Apparently, we have to be well versed in every single field so that we can make sure that our particular calculus course is relevant to each individual student and their future studies. This is a task that I refer to as, what's the word that I use? Impossible, because I've got no way of knowing. Because in addition to trying to customize this class for 40 different people, I'm not allowed to look into the future and see what you're going to be doing. They're like, oh, okay, I will customize this class. So for each individual student, I will like look into their future, tell them what they're going to be doing and say why this. Then they're like, oh, Leach, you can't do that. I'm like, oh, what? You're going to break the timeline if you like look into the future and give present students information about their future selves. It's like, oh, but some of them could just drop out right now and start having fun. I'm like, well, you can't tell people that. I'm like, oh, we'll see if you still have that same opinion in 6 months. Spoiler alert, you don't. Just kidding. They totally did. It just wasn't relevant because they got fired. I'm just kidding. That's not what happened. That was only one possible future of many that I looked into. It really bothered me, by the way. Spoiler alert, this movie came out a long time ago. So if you're not caught up on the MCU, I mean, I'm sorry, but it's like Darth Vader is Luke's father. That's not a spoiler. That movie came out in 1981. If you haven't seen it by now, you don't get to have that spoiler. Do you know what I mean? There's a statute of limitations on this shit. And you have passed it for Empire Strikes Back. Darth Vader is Luke's father. I just said it. Don't at me. All right. So Doctor Strange looks at 14,065,000. That really bugs me. Because he like hits 14 million and just goes 65 past that. I mean, they wanted to make it a big number, but it was like a 14, then 3 zeros, 4 zeros, then a 65. Wasn't it like 14 million? I remember it was no thousands. And it just, I don't know why that number bothers me so much. Because they wanted to make it big. So they're like, well, go into millions. Yeah. And they're like, oh, yeah, 14 million. But he couldn't just say 14 million. They wanted to have like a little Spock moment where he's overly precise. Right? And so he's like, oh, I looked into, because the dude's a doctor. He should understand numbers. He could have just said 14 million. Who cares about the 65 at the end? Do you know what I mean? You're just trying to be overly precise, and the writers failed at being overly precise. Now, if they wanted it to sound like a Spock moment, and you wanted to make it overly precise, then don't just be lazy and tack on another 65. I've looked into 14,307,065 possible futures. Right? Now it sounds overly precise. The 65 at the end, that just makes it kind of bullshit. Because any reasonable person in that situation would have said, I've looked into over 14 million. That's like asking, what's the price of this fabulous home here in Burlingame? And say it's 14 million and $65. At that point, I would just walk away. I don't care how much money I actually have. I'd be like, oh, no. Not because I wouldn't be I would be bothered by an additional $65. But I promise you, my offer will be 14 million. And if you argue with me on this, I am going to buy your entire business and ruin you. Do you know what I mean? Now, if I was buying a house from Dr. Strange and he said the price of the house is 14 million and $65, I'd be like, oh, nice callback. I will take it. You know what I mean? But this is exactly why I didn't buy the $14 million mansion in Burlingame, because they're like, well, it's 14 million. I'm like, oh, nice, I'll buy it. And $65, nope, walked away. Do you know what I mean? Anyway, it bothered me that they put 4 zeros in that number and didn't just have them say over 14 million. C-3PO did the same thing. I don't remember the exact number, but the problem was he used an exact number. The probability of navigating an asteroid field is approximately, and he says approximately 4,000 to 1. But like an idiot, because he doesn't understand numbers, he's like, oh, approximately 3,857 to 1. It's like, oh, number one, there's no way you can state that number with that much precision. If they went with 4,000 to 1, it'd be like, oh, all right. But to state it with that precision, and no, that's just not how probability works. Do you know what I mean? I'm saying this because some of you might be writers in the future and just gonna like barf out some numbers that don't make any sense whatsoever. What we're talking about? Oh, yes. I don't like it when there's like extra precision. Too much precision means there's no precision. You're just making shit up and it becomes suspect. Like if I said my weight is 220 pounds, it's like, okay, that's reasonable, 220. If I said it was 222, that tells you some additional information, right? If I said my weight is 222 pounds, you could probably make some inferences about why I would pick 222. Because the fact is, 222 pounds, if that's your weight, you're 220 pounds. Just because it's going to be plus or minus, it's going to go up and down. But if you're like, oh, the person's mass is 221.8794 pounds. It's like, oh, that's a bullshit number. That is a bullshit number. Because if you want to change that number, here I go. And I've just changed that number in those thousandth places. It's gone too far. You know what I mean? Plus, if I want to make that number go up, I'll just eat a salty meal and then tomorrow it will be higher. You know what I mean? So when someone gives you their weight and they're like, oh, 222 pounds, you can make some inferences about what they're going through. You know what I mean? But if I was to list my weight, if I went to the driver's license place and they said, list your weight, first of all, I'd be like, oh, 200, because then, I mean, are they going to check? I actually wanted to go in there and put 350 to see if they even notice. You talking about? Oh, yes. Oops. Don't use the wrong pen on your rocket book. I'm glad I recorded my problems with Doctor Strange. MCU, if you're listening. Disney is probably listening. So I'm probably banned from Disneyland. Disney is like, they're going to be complaining about me. So I'm going to have a sit down with the administration. So, well, you can't insult Disney. Michael, but they're greedy assholes. Michael, see, you got to stop doing that, especially when you're being recorded. I'm just kidding, Disney. Keep making movies. I know you're going to anyway. Incidentally, the actual thing they should do if they find themselves being insulted, realize that they're Disney and I'm just some Yahoo out in San Bruno of all places, and just ignore it. That is the best response to being insulted. Just walk away. No response is best response. Here's another important thing that the derivative will tell us. The sign of the derivative, I'm going to actually start using first and second and whatnot, but the sign of the derivative tells us if the function is increasing or decreasing. I summarize this by saying that the sign of the derivative tells us the direction of the function. The sign, positive or negative, of the derivative f prime tells us the direction, increasing or decreasing, of the function. Sign of the derivative, f prime, tells us when the function is increasing or decreasing. It tells us the direction of the function. I'm going to use the example probably everybody uses. Why do I always make the parabolas too small? It should be like twice as big. Because I used a half mark, not just full marks. Use full marks. Be brave. 1, 2, 3, 1, 1, 1, 1, 1, 1, 1, 2, 3. So if we think about the easiest function that has more than one direction, f of x equals x squared, we would say that f is decreasing when x is negative, and f is increasing when x is positive. F of x is flat when x equals 0. So that's the direction of our function. We would say f is decreasing when x is less than 0. F is increasing when x is greater than 0. We're just reading from left to right, and when x is negative, our function is going down. It's flat when x is equal to 0, and then the function is going up when x is greater than 0. And when I say f is flat when x equals 0, that means at x equals 0, the function is neither increasing nor decreasing. In this case, we can see that the function is changing direction at 0. But we don't just want to say it that way. We want to indicate that it's flat. It might not be changing direction. Just because a function is flat doesn't mean it's changing direction. In this case, it did. That's not always the case. We can't read that the other direction. If we look at the derivative of this function, we get 2x. X is just a line. When x is negative, 2x will also be negative. When x is positive, 2x will be positive. So the derivative f prime is negative when x is negative, and f prime is positive when x is positive. And f prime of 0 is equal to 0. If we think about what the derivative is telling us, the slope of the line tangent to the function, we can see why this relationship is going to exist, that the sign of the derivative will tell us about the direction of the function. If I look at the tangent line, when x is negative, my tangent line has a negative slope. That makes sense when we look at the function, or the derivative, 2x. 2x is negative when x is negative. The slope of the tangent line is negative. That indicates a function that is decreasing. That's a slope that is negative. I tried to write an m, that's not a 3. Here, I'll put a little tail on it. There we go. On the other side of 0, if we look at the tangent line there, it's going to have a positive slope. Positive slope means an increasing function. Negative slope means a decreasing function. The sign of the derivative tells us about the direction of the function. This is going to come up later on when, not today, because I clearly talked about the MCU a little bit too much. Talk about it today. This is going to be useful if we want to find a maximum or a minimum value for a function, because some evidence that the function might be changing direction is when the derivative is equal to 0. In this case, when the derivative is equal to 0, the function goes flat. The function is neither increasing nor decreasing. There is a chance that the function might be changing direction. If it's decreasing, then goes flat, then increases afterwards, we can say we've hit a minimum. Or if the function is increasing before it goes flat and then decreasing afterwards, we've hit a maximum. But it might be that the function is increasing, then goes flat, but then just continues to increase, in which case we've not hit a maximum or a minimum. The function just went flat and then continued to increase. It got tired, took a little rest, and then went back to its increasing ways. So this is what we want to think about. We're going to have exercise on this tomorrow. We're going to be looking at some derivatives and seeing what they tell us about the function, then looking at some functions and seeing what that tells us about the derivatives. Any questions? Comments? Not remarks. All right, that's it for today. I will see you all on tomorrow. Everybody have a good day, and thanks for playing.